Morning, everybody. We get to put up with booming noises apparently this morning. I have no idea what's going on out there. They didn't send us any information. I did just go and check, and there is a very large piece of equipment there taking out concrete. So I do apologize. It's not my fault, and we'll try to continue on. And I know it's distracting, but we'll try to do our best. Few items of just organization, business, that kind of stuff, right? Chapter 1 homework happened, or at least the first part of Chapter 1 homework happened. This week is about Chapter 2 and the second half of Chapter 1, and really getting started on Chapter 3, because this Wednesday, we will have a lab, our kind of first lab with actual equipment in it and running through the lab process. A week from Thursday, we're taking our first exam. I'm kidding that. I know, it feels like it just comes by so fast, right? So if you are feeling like you're behind or whatever, messed up on the first homework, I really suggest you focus on Chapter 2. Chapter 2, I feel like, is where a lot of this class really begins. So be mindful of that. If you're drowning, if you feel like you're not keeping up, you've got to get a hold of me right away, right? We can fix things now. It's too late to fix things right before the exam is happening. Some of you learned, I guess, a little bit the hard way. I apologize. Thought I mentioned this. I don't check email over the weekend. I really don't even check email after 2 o'clock in the afternoon. There's usually about a 24-hour cycle, and in a 24-hour period, I'm checking email mostly between like 11 and 1. I'm really active. When I get emails, I'll check them in the morning. I'll triage them for things that I can answer later versus need to be answered now. But really, in this class in physics, there really aren't any emergencies. There's typically time unless you've decided to wait until Saturday morning, right, to start your homework, in which case, good luck, right? I've been asking you to be ahead of these things and doing it every day and being involved, and that way you'll know Tuesday, Wednesday, Thursday, if you need help, and I can answer stuff in email Friday during grass, right? So that you're just finishing up stuff for turning in on Saturday. Or even ideally, I had people in grass come in and finish their homework and walked out, right, by 9 o'clock in the morning Friday, physics homework done, right? And that's awesome. Right? You got other classes you can focus on, work to do, that kind of stuff. So do be realizing you've got to be in that mode, right, of being ahead of the game as much as you possibly can. All right. Today, we're going to take what we learned last Thursday about motion in one dimension with that toolbox and that problem-solving method, and we're going to turn it 90 degrees and just be dropping stuff or throwing stuff into the air. So we'll do the vertical version. And then we're going to loop back to some of the Chapter 1 content where we have to talk about a special mathematical property called a vector that we're going to be using for the rest of your physics career. So let's do that, okay? And just as again, try to help you understand the kinds of things that you should be ready for when you're coming to lecture, because ideally you've looked at the chapter content, you've watched some videos, you've done something to introduce right there. I want you to, this isn't a quiz, we're not going to do the formal quiz paper or anything like that. But what I want you to do, okay, is just take a look at this question. I expect you to be able to define what free fall is. And maybe get some insight into my sense of humor. So what's the answer? Say it out loud. Good, strong and wrong, right? Don't be afraid to be wrong. You want to be making as many mistakes as you can right now, right? So that we're not making those mistakes later on the exam. So free fall, by definition, in mechanics, in physics, is motion where gravity is the only force acting on it. We're really not going to get to forces until chapter 4, believe it or not. But you have experience with gravity. So if something is falling, right? Something is in free fall, like this ball. Is that ball in free fall when I let go of it? Okay, good. What did you assume if you answer yes? That there's no, what's the thing that could be not gravity that's acting against the motion of the ball?
Air resistance.
Okay, that there's no air, right? So what I want to do is I want to do a little bit of an experiment. I'll use this. Those are my notes. I need the reference though. Let's get this one. Yeah, Physics 2B folder. They don't do that. Okay. So, a little experiment here. Papers inside. There we go. All right. So, if I take both of these objects right here, okay, a folder and a piece of paper, okay, and I hold them at exactly the same height, and I let go, same time, which one's going to hit the ground first? Binder? But I thought free fall was gravity only. What's the one thing we can't get rid of in here? Air resistance. Okay. So, see what happens. Okay, good job, right? You predicted correctly what was going to happen, right? And so this is definitely not free fall. So in order for this to be free fall, what do we need to do? We've got to remove everything that's not gravity, right? Okay, so two choices. We go talk to Elon Musk, we get a ride on the next Starship, or we suck all the air out of this room. I think option number 2 is less expensive. So how good are you at holding your breath? It'll take me about an hour and a half to evacuate all the air out of this room. No? No, let me go get the vacuum pump. You can't see it, but it's down there. That's a vacuum pump. Okay? And somehow I can plug it in. All right. It makes funny noises. Right? Okay. Now this isn't like your vacuum at home. Okay? This pump is actually capable of producing a vacuum that is very similar to where the International Space Station orbits. Okay? Got to give it enough time to do that. This pump probably take about 3 days to evacuate all the air in this room. Okay? That's assuming we could make the room a vacuum tight space, which it isn't. So instead, I brought a little bit of a smaller room here. Okay? Right? Plexiglass tube. And inside this tube is a piece of styrofoam and a penny. And I don't know if you can see that in the back, but the people up in the front can, right? As I turn this over, which one gets to the bottom first? You see it? Which one's hitting first? The penny's hitting first, right? Piece of styrofoam is lagging behind. Again, it's lagging behind because of air resistance, right? So what I'm going to do is I'm going to take all the air out, or at least the vast majority of it. Assuming I can get this thing to fit. Okay, I'm going to hold on to that. The piece of styrofoam gets sucked onto the plate. You like the funny noises it makes? Right? You can kind of tell when it's done because the funny noise stops, right? The gurgly noise. Okay? Alright, so I'm going to assume that all the air is out of this thing. And I'm going to do my best to flip this over, right? And again, we may have to rely on people in the front to see what happens. Set. Okay, here we go. Actually, it looked like the styrofoam hit first that time, right? What happened is the penny bounced. They're hitting at exactly the same time. Okay? Again, compare and contrast with the styrofoam lagging behind there. Okay? And you can see that when we can eliminate everything except gravity, we can get things to fall at the same rate, okay? And that's one of the features of free fall. Free fall, that definition of gravity being the only thing that's acting on it, means that all objects are going to accelerate at exactly the same rate, okay? So I got funny with my animations here, right? But the acceleration that anything is going to experience, doesn't matter how big it is, doesn't matter what its mass is, doesn't matter what its political preferences are, it's going to fall with that acceleration. Remember, acceleration isn't speed. This is how much the speed changes. So if I drop something, dropping means that it starts with zero velocity, okay? About a second later, if it changes about 10 meters per second, right? So for every second that goes by, the speed is going to change by about 10. 1 second later, how fast is this ball going? About. It's 9.8, it's about 10. Right? And then a second after that, how fast is it going to be going? Every second, how much does it change? About 10, right? So the first second, it'll be 10 meters per second-ish. The second will be 20 meters per second, 30 meters, right? So on and so forth. But I can fix this problem. Remember this problem where air resistance is in the way? Okay? I don't even have to ask you to hold your breath. Okay? I'm going to do a physics trick to make sure that both of these things hit the ground at the same time. You ready? What did I do? I made sure that the thing that was causing the difference was exactly the same for both of them, right? In effect, I made the air resistance the same. So while this isn't strictly free fall, since the binder is less affected by the air resistance, I took advantage of that. One of the things that we'll do in this class is we are going to ignore things that we don't want to deal with, okay? We're going to ignore air friction quite a bit. You'll see problems, you see me mention it. We'll say something like ignore air resistance. Or they'll say an object is in free fall. And what you're supposed to do at that point is not worry anymore about air resistance. What's the only thing you're going to worry about?
10.
Gravity, the 9.8, the 10, right? Okay. And which way does gravity point? The answer is in, but down works well enough, okay? Because if you go to Antarctica, from our point of view, it's pointing up, but it's still down for them. We'll get to orbital mechanics later, okay? But you've got to realize that we are simplifying. Why would we throw out air resistance? Hard, okay? It's hard, and this is baby steps into physics, right? This is introductory physics. We're trying to not completely blow your brain. Well, we're doing that, but not yet. Okay. I did have a video in case my demonstration didn't work, but we'll stop. We'll go past that. And then, do I want to do this? Did I prepare you adequately for this quiz? I think I did. Yes. Let's do a quiz. Quiz sheet's out. Pause that. Okay. So what I want to do is we're going to do this problem, okay, as an example. But before I get into the problem, I do want to get the toolbox onto the board. I'm not going to write it on my iPad this time, okay? But yeah, I lied. I am going to write it on my iPad. Because I have this power. Let's do this, this, and this. Okay. So, you remember the toolbox from last time?
Yep.
Right? The kinematic equations? We're gonna turn them sideways. and not really change anything. That was our first equation, wasn't it? But we're going to pull a little trick. And this is actually something your book will introduce you in chapter 3, but I'm just going to introduce it now, okay? Because it's handy for keeping track of what's going on, okay? I can put y's on all the things that have direct. Time doesn't have directions, okay? But everything else can, right? So if I write Vy, what am I trying to say? What's the long version in English of what Vy means? Final velocity in the y direction. So what does V naught y mean? Initial velocity in the y direction. Just trying to really reinforce that we are thinking in terms of up and down now as instead of right to left. So I could have drawn the toolbox last time with a bunch of x's in the bottom, but I didn't want to overwhelm your brain with the first pass. And then ay, right? Okay, acceleration in the y direction. Good, this is important. You might think, well, Mr. Bayless is stupid and pedantic, why are you treating me like an idiot? You're going to forget. You're going to be sitting there going, wait, what direction am I doing? Because in chapter 3, guess what we're doing? We're putting x and y together, right? So it's important to keep track. All right, so the second equation, I don't know if you remember, started with delta x. So what can we write instead? Oh, delta y equals v naught yt plus 1/2 ayt squared. That's an a. Are these different tools? I heard that. You want to think of them as different tools, but they're not. They're the same hammer, same screwdriver that we had before, different color handle, okay? But they do the same things. Now, one of the pieces of violence, one of the terrible things that a physics textbook will do to you, is they will write, I think this is what they wrote in your book, v equals v naught minus gt for the first equation. Now that does look completely different, doesn't it? It's not. What did the author of your textbook do? Replace the acceleration with its proper direction. Which way does the acceleration point? Down. And what is that acceleration for something in free fall? It's little g, right? 9.8. So, point of clarification. Little g is a number. It just means 9.8 meters per second squared. The negative sign, that's a direction we're going to assign to it. Okay? But little g is not equal to negative 9.8. Little g is just 9.8. Okay? All right. And then the author, delta y equals v naught t minus 1/2 gt squared. Again, what happened here? They just put it, right? So unfortunately, as a newbie, you come up against this and you are now thinking, oh my gosh, there's not just 3 equations, there's 6. I didn't write the last one, right? Okay? And you're thinking them as separate things. They're not. They're the same thing. Which is why I write mine like this. Because I can remember 3 things. I can't remember 6. And I don't need 6 things because it's the same physics. Doesn't matter if it's moving horizontally. Doesn't matter if it's moving vertically. I can approach it exactly the same way. And so here's an example of where I'm practically begging you to think of these. That's not what I wanted to do. Sorry. The 2 buttons are really close to each other on the screen. I want you to try to not focus on details right away. Take that initial step back and look at the bigger picture, right? Kinematics, the kinematic equations can handle anything, right? They can handle, as long as our acceleration isn't changing, we're good to go with these 3 tools. Whether it happens vertically or horizontally, there's devil in the details there. I give you that. But try not to think of them as different things. they're two examples of the same. So let's see what we can't figure out with this. Okay, so first things first though, we need to visualize, right? Okay, which means I now need to draw a picture of a hot air balloon. Lucky for me, the internet has clip art. Okay, so we'll just, there we go, hot air balloon, right? Let's see, what's something we know about this hot air balloon? We know that this hot air balloon is going upwards, right? 4.3 meters per second. All right, and what do we know about how high the hot air balloon is above the ground? 56 meters. Okay, and we know that there's a bowling ball. Notice here, in my visualization, I've chosen to have a picture. Sometimes I can visualize it and draw a rudimentary diagram, right? Other times I'm stuck with a list and I just have to start with a list and see if I can't come up with something, right? So again, however your brain works, organize the information that you're given as best as possible, right? Okay, so I'm still visualizing. What is this bowling? What speed does the bowling ball start at?
0.
Oh yeah, why did you say that? It says it's dropped, right? But the problem is it was dropped from something that was moving. So how fast is the bowling ball really going? 4.3 upwards, isn't it? So even though this problem says the bowling ball is dropped, it's dropped from a moving object. If you are, don't try this at home, but if you're sitting on the hood of a car, driving at 20 miles per hour, and you throw a 50 mile per hour fastball, how fast is that ball really going? Your 50 plus the 20 you were already going gives you what? 70 with respect to the ground. The measurement of 56 with respect to the ground. Acceleration with respect to the ground. So this bowling ball is really moving at 4.3 meters. Tricky, right? Mr. Balogh, there's no way I would have realized that. Welcome to class. What am I trying to show you? Now you've seen that, right? So now you're going to be primed for making sure that you understand what these motions are. And what are the chances that you're going to nail exactly the right visualization every single time on your homework? First try. Probably not good. And it's not because you're stupid. You're not stupid. You're amazing. But if you're sitting there all alone, or worse than alone, you have ChatGPT, how are you going to be able to check without trying the problem and failing? How do you fail faster? How do you check to see if your visualization is right? There's a better way. Can't think of it? You're going to ask somebody else. Another person in the class. Hey, have you tried this one? What did you get? What did you see? What's your visualization like? Now, I know I overheard that there's a Discord going, which I think is fantastic. I do not want to be invited to it. Not because I don't use Discord, I use Discord every day. But because I've noticed that as soon as Mr. Balogh comes to the Discord, everybody stops talking. And I want you talking to each other, right? Iterate as fast as you can on making mistakes, right? Bounce ideas. How did you set this? What's going on, right? So that you can make all those mistakes you need to make. You're new at this, and that's okay. And you're not stupid. You're amazing. Leverage these technologies that we've got to communicate with each other, but make sure you're communicating with each other and not Google, not ChatGPT. They just don't know. All right. So let's make a list. Vy, V naught y, Ay, T, delta y. I didn't write the other one up here. Where did I get that list from? Yeah, kinematic equation. Is it a brand new list?
No.
I'm gonna rewrite these in what I call their proper form. Plus 2ay delta y. Okay, those are the ones that I wrote on the other screen. Okay, so I got these directly out of this list. The only change to them is I'm putting the y's on there just to remind me that I am doing an up and down problem. Okay, but this basically is the whole list of everything I could know and not know. The ball, for clarity, I'm going to draw this, but this isn't actually kind of what, it doesn't have any sideways motion, right? But if I just drew the ball going up and coming straight back down, it would look like that. It's no good. Okay, so do we know how fast the ball is going right before it hits the ground? They don't tell me any information for how fast the ball is going right before it hits the ground. Okay, no. Do I know how fast the ball is going when it's let go? Yeah, we just established it's not 0, right? Okay, what is it? Okay. You're going to leave a space between the equal sign and the number because I want you, from now on, to always put a sign on the number. What direction is this thing pointing? Positive. It starts by going up, right? So the initial speed isn't just 4.3, it's positive 4.3. If you don't put the sign on it, it's positive. I know. But that positive sign, when you're coming back later to troubleshoot, your brain's gonna be able to attach to it. If it's just kind of blank there and implied, you may not think about it. You gotta think about directions. Okay, acceleration in the y direction. Okay, the number's 9.8, but you're going to leave a space and you're going to think about the direction it's pointing. Which direction is the acceleration pointing? Okay, what's causing the acceleration? Which way does gravity point? Until chapter 4. Do we know how long it takes the ball to do anything? Nope. They don't tell us. And do we know the total height that the ball fell through? Okay, so what are you going to do? You're going to leave a space. You're going to write 56 meters, and then you're going to go back and you're going to ask what? Which way does it go? It's displacement. Where did this thing end up? Lower than where it started. I love the sound effect. Thank you. Okay? It ended up lower than where it started. Started up here, went down. What direction is down? That sign right there is one of the most important signs in this class.
Are we assuming that that's like the max height that it reached? Because if it was dropped from 56 but it's going up, it would hit like 50 or...
Right, it's going to go up and come back down again, right?
Right.
But they didn't ask me any of that, and they didn't tell me any of that.
Right.
The kinematic equations, no.
Okay.
Yeah, it did. Yeah, it's a good one, right? Is this thing a max height? No. What is the max height? I don't know. Do I care? It's not asking me for it. Can the kinematic equations figure that out? Yes, they can. If you give them the right information. Let's say for a second that you nailed the positive 4.3 and you got the negative 9.8, but then you just dropped 56 into that answer right there, instead of considering the direction. What would you have been telling the toolbox about the motion of this ball? It starts going up at about 4 meters per second. Every second, its velocity is going to change by negative 10, right? So that means a second later, its velocity should be like negative 6, right? And that it's going to end up 56 meters higher than where it started. What are the kinematic equations going to say? What are they going to do? They're going to give you nonsense. You gave them nonsense, they're going to give you. You're probably going to get a square root underneath a negative sign under a square root, and it's going to give you imaginary answers or something, right? Okay. It goes wrong really fast. Think about the data you are giving. How much math have we done in the last 20 minutes? 0. This is where this class lives and breathes. In the visualization and the strategy. The math is a secondary thing. Important. but secondary. Don't start with math. Okay, that negative sign, negative 56, right? You're gonna come to me on the homework. Man, why you plus hates me? I know I'm doing it right. The red box. And I'll take a look at your work. I was like, oh, we didn't put a negative sign in your delta y. And you will look at me and say, Mr. Balogh, I have worked on that problem for 3 hours. You trying to tell me all it was a minus sign? I'll be like, yeah. It's the minus sign. To end all minus signs. You'll come up to me on an exam. Mr. Balogh, I didn't do everything right, I just got the negative. I was like, yeah, you got the physics totally wrong by missing a minus sign. And you'd be like, Mr. Balogh, extra partial credit. I'd be like, you didn't think about the direction. It's important. And you'll go away disappointed because I didn't give you credit because of a minus sign. It makes all the difference in the world about the physics of what is taking place. So, how are you going to learn to not make that mistake? Go ahead and say it.
Visual.
By making the mistake. Hopefully these things keep you there, but you're gonna make that mistake, right? And are you gonna sit there and wallow in self-pity about how stupid you are? No, because you are brilliant and you are amazing and you deserve to be here. It's not your stupidity. It's because this stuff is tricky. And because you gotta think and you gotta make those mistakes so you can learn to not make those mistakes and start learning that process of checking. And please, 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 help each other. Make mistakes faster with each other. Right? That's how you're gonna succeed. Okay, so now that we got all this, we can strategize. And what's our what did we say? Okay, part A. How long? Oh, so what are they asking for? Time. Okay. And so we'll circle that one. And okay, so what does my equation not need in it? What do I not want? What tool do I not want to use? What do I not know? The final velocity, right? Vy. Well, the first equation has Vy in it, doesn't it? And the third equation does, so let's avoid those. What about the second equation? We okay? Do we know the delta y? Yeah, do we know the v naught y? Yeah, do we know the t? No, but we want it, right? We want to solve for it. Do we know ay? Okay, so this has got our unknown thing in it and everything else is known, right? So a strategy could be, not to write in your highlighter, use second equation, solve for t. Alright? Okay, write down your plan so you have breadcrumbs to follow when you go back. So what's the second equation? Delta y v naught y t plus 1/2 a y t squared. Okay. What are we going to do now? Math, right? We're actually going to do the problem now. Everything's been set up to this point. Minus 56 equals positive 4.3t minus 4.9t squared. Where did the 4.9 come from? What's 9.8 divided by 2? 4.9. And then the negative side comes along to the right. This is quadratic in t. It's t and t squared. Remember you had to solve a quadratic equation for your math review? Well, this is why. One of the reasons why. Okay? So, when you solve this, not going to do it because it's math. You don't want to waste time. Negative 2.97 and 3.85 seconds. 2 answers. Okay? We're not going to get into it right now because I don't have time, but I'm going to go ahead and pick the 3.85. It's not entirely safe to always pick the positive answer. We'll talk about this next in chapter 3. But for now, negative time seems a little bit nonsensical. So 3.85 seconds, right, is how much time this thing was in the air. As far as the check is concerned, independent of Wiley Plus getting a green check box, There is another way we could have done this problem and avoided having to do the quadratic equation. What's a plan where we could not use the second equation? Ooh, use the third? Okay, but we don't know Vy, right? We know initial, we know Ay, we know delta y, don't we? So what can the third give us? It can give us Vy, and then we can use the first equation to solve for t, right? And we avoid a quadratic. So different plan is use third equation, whoops, solve for Vy, use first equation, solve for t. Sorry about my bad handwriting, okay? So, two different ways, and this would be an excellent check, right? Because if you get the same time, you get that 3.85, right? Then you know things are working out, right? But you could also avoid the quadratic way. It just requires more algebra, so pick your poison, right? Quadratic equation or doing more algebra. All right. That is the end of chapter 1. Oh my gosh, it took forever. Let's speed run the second part. Sorry, that was the end of chapter 2. Let's speed run the end of chapter 1, right? This part of chapter 1 that I'm saving for now, because what I want to do is teach you what a vector is, so that on Thursday we can go in and get into chapter 3, which is using vectors with everything that we just did, okay? Now, I do need to apologize in advance for the mathematical nature of what I'm about to talk about. A vector is a mathematical thing. It has very real physical application, but I do need to teach you some math. And I've noticed that I'm not a good math teacher, a good physics teacher. I'm not a good math teacher. And usually what happens about 30 seconds to 5 minutes in is people shut their brains off, right, when I'm teaching math. So I'm going to get really desperate at certain points here, okay, to try and maintain your attention. So bear with me. There might even be a dad joke. No promises. What's a vector? Yeah.
I've got two possible definitions.
Okay.
Definition possibility number 1, it's something that contains a direction and then a magnitude.
Okay. I like that one.
Other option is just 3 numbers that could translate to coordinates.
Okay, well, that's the same thing. Or, as most biologists knows, it's the thing that causes disease or transmits it. Not that one, okay? So, in mechanics, which of these things are vectors? So a vector is something that has direction along with its magnitude, its number, where the direction has essential meaning. Is time a vector? Does time have a direction? That was a trick question. Physicists are still arguing over this one. It seems like, yes, time does have a direction, but you can't go backwards in it. Does mass have a direction? Well, mine happens to be increasing over time. But, okay, but mass itself doesn't have a direction. What about speed? Does speed have a direction? No. But velocity does. What is velocity? It's speed with direction. So speed is simply how fast something is going. I'm going 45 miles an hour. That's different than if I told you I was going 45 miles an hour north on Blackstone. Right? There's a difference, and the direction matters. Okay. Displacement. Is displacement a vector? Yes, it has direction. What's the thing that's like displacement but doesn't have any direction? Distance, right? Distance is what we would call a scalar. Scalar, by the way, fancy mathematical term for a thing that's not a vector. Okay? Is an elephant a vector? Probably not. Although, I would be interested in what direction the elephant's running. Towards me or away from me would be critical information. Okay, is force a vector? Yes, forces have direction. So you want to key in on direction, right? Does the direction matter for these things? And how do you know if it matters? Again, by experience, by making mistakes, right? By doing it. So, is an arrow a vector? Trick question, sort of. Because vectors visually are arrows. This vector has a length and a direction that is pointed. What can you tell me about this vector? Is it the same vector? Why not?
Different direction.
Different direction. Looks like it has the same length, right? But it has a different direction, so it's not the same. This vector's name might be Alice. And this vector's name might be Bob. Okay? They're different vectors. They have the same length. Now notice how I'm writing those vector symbols down. How do I communicate to you that Alice right here is a vector? I drew an arrow across the top. And in physics, that arrow looks a little bit funny, right? That right there is a scalar because there's no vector symbol above it. Technically, we should be drawing like an arrow like that, but physicists are lazy, and if we cannot pick up our pen top, we won't. Okay? So we often only draw one half of the arrowhead, right? So just that's how the notation works. You'll see it online. You'll see it in some of the older books. Instead of using the arrow, they'll use bold-faced type. They'll write a bold letter. Do you have bold-faced pencil? No, right? So just drawing that arrow symbol over the top, right? So if I wanted to talk about the length of Alice, I could either just write A. Sometimes you'll see they'll write absolute value signs around the vector sign. They're trying to communicate that is the magnitude of the vector, just the length, right? So what can we say about Alice and Bob? Their magnitudes are equal, right? But as vectors, they are not the same thing. Okay, and then along comes Claude. Okay, what can you tell me about Claude? Same direction as Alice, right? Okay, so their directions might be the same. What can you tell me about their magnitude? About how small? Be generous. Half as long, right? Okay, so we could write that Claude is half of Alice. And by writing that, what do we automatically know about Claude and Alice? They're the same direction, but Claude's magnitude is half. It's not that that's half the direction, right? It's half the magnitude. Okay, and then along comes Denise. Okay, now what can you tell me about Alice and Denise? They're the same magnitude, but different directions. Yeah, opposite directions. And the way you indicate an opposite direction is by throwing a minus sign on front. So what I'm doing here is I'm laying down. So when you went to kindergarten or first grade or wherever it was, right? How did you learn how to add 1 plus 1? Right? You teach it. This is a 1. Everybody say 1. 1. Right? And this is a 1. Everybody say 1. 1. Right? Okay, what's this? 2 1s. Right? Like, you learn kind of by doing, right? By doing a lot of those papers that you would turn in and get the gold star on or whatever, right? I always failed them. I'm horrible at that. Okay? So you, step by step, went through this process through grade school of learning that 1 plus 1 equals 2, and 2 plus 2 equals 4. And if Alice had 5 apples and Denise comes along and steals all of them, like, that's capitalism. But like, we need to do the same thing all over again. And we don't have your entire life to do it, right? Okay, we got less than 15 minutes. So, how do we do this? Okay, first of all, to work with vectors, I can already tell you, I've lost you. It's because it's all mathy and stuff like that. So, over the years, I've just developed these things, and this is one of the things that really starts to just make people pay attention. I figured that if I can make myself look as bad and as foolish as possible, that you guys will pay attention, right? This is my vector hat, okay? It comes out whenever we're dealing with vectors, so I essentially like wear it all semester long, okay? Right, okay? It's good, right? Does the thing, and then it's got two pins. One says, I'm a scientist, let's experiment. And then this says, welcome to Endor, visit the Forest Moon. Star Wars reference. But yeah, if anything I can do to maintain your attention, maybe the faster that I walk, right? The faster the thing you will spin, right? But we need to talk about the pieces, parts of vectors. To be able to pull off math with vectors, to be able to do something, like, say, add two vectors together, right? What the heck does this mean, right? I know what 1 + 1 is, Mr. Balogh. How do you add something, right? Like this vector A plus this vector B, right? Like, what does that mean? Well, it literally means do A, then do B, and you end up with a result, a resultant, okay? The resultant always starts where you start with the first vector and ends where you end with the last vector. But to be able to do this mathematically, like be able to turn the crank and do the actual numbers, you've got to break a vector up into its component parts. The components of a vector, let's just look at Alice right here real quick, okay? We can always write down the components of a vector no matter which way the coordinate system is pointing or anything like that. We'll start standard. But Alice is going to have an x component. The amount that Alice lies along the x-axis, and Alice is going to have a y component pointing up the y-axis. In physics, we tend to draw these components coming from the origin. You can also draw them over here. This is exactly the same thing. But notice, these components are always what with respect to each other? At right angles. So they form a right triangle. And if we know the angle that Alice is pointing, what trig function are we going to use to find AX? How'd you do that? It's touching the angle, right? So it's going to be Alice's magnitude cosine theta. And what's AY going to be? Sine of the angle. This is why I taught you touching, not touching. You're going to be able to really quickly find the components of a vector, even if, for some reason, the coordinate system gets wonky. And we have components, say, going along that direction and that. You're like, Mr. Balogh, why would you ever do this? This is insane. Welcome to the universe. This is what the universe does. Okay? So, how do I know what this component is going to be? Is it touching the angle or not? Touching the angle. What is it? Cosine. And the other one's going to be sine. The components of a vector. So now it won't go away when I push it. The components of a vector are the parts that form the right triangle. And those components have to lie along the x and y axis of whatever coordinate system, however it's rotated, whatever it's doing, right? So here we've got our breakup, right? But over there they just drew a different picture where instead of AY being drawn along the axis, they just completed the triangle over there. Either way you want to do it's just fine. Vectors can be picked up and moved around anywhere in a coordinate system they're the same exact thing as long as you don't change their length and you don't change the direction that they're pointing. They're exactly the same thing. So, we're running out of time, so let's not do it as a quiz, but I'm gonna make you talk to each other, okay? So you don't need to do the papers and that kind of stuff. What I want you to do right now is look at this, and with your neighbors, determine which of these answers is correct. The angle is beta right there, and I want you to determine the correct sine and cosine and direction for the components of that. As soon as you've thought about it, feel free to turn to the people around you and start talking about it. All right. Let's do EX over there, right? Did you notice that the X and Y directions are not what you're used to getting? Previews. Spoilers. Okay, so X is down that way, Y is down that way. EX, sine or cosine? Why is it sine? It's not touching the angle beta. Just do that. You're going to get it wrong if you do it any other way. Really. Okay? EX is not in contact with that angle beta at all. So you know you have to use sine. Okay? And it's going to be E sine beta. You know that for EX. Okay? What about EY, sine or cosine? Why is it cosine? Because it's touching the angle beta, right? E is the hypotenuse, and the two components are the right legs of the triangle. Okay, so we've established EX has to be sine, EY has to be cosine. What directions are they pointed? Positive X and positive Y. I know you're sitting there, down. That's positive X, that's positive Y. So they're both pointed in which direction? Positive direction. So now we need the choice that says that EX is sine, but it's not A, B. It's that's correct, right? Yeah. And then I don't have to check the rest because those are all negative. It's got some versions of negative in them.
So if the direction is pointing down, but it's given to us that it's in a positive direction, do we use that?
Yeah. I'm showing you something now for the next till after exam 1, we're going to make sure up is positive and right is positive. But as soon as we get to chapter 4, we're going to start changing that. I do try to prepare you for what's coming up. Okay, the answer there would be that. Okay, so let's quickly do how you work with vectors. And I kind of blew over it, it's very important. The reason you want to know the components of a vector is because when you add vectors together, their components add together. So you can't just add Alice and Bob together. You have to take Alice's X component and add it to Bob's X component. And then Alice's Y and Bob's Y. Those things can add. components can add. The actual vectors themselves can't do that directly. So we've got a situation. We got to start. Oh, and you're going to learn your compass directions apparently. Which way's north? There. South is opposite. Which way's east? And west. Okay. Standard compass rose right there. Okay. So hiker walks due north. So they go that way 3 kilometers, right? Okay. And then she turns towards the east. So which direction is she turning? To the right. Okay. How far does she turn? 20 degrees and walks 2 more kilometers. This can be hard, but she turns 20 degrees from the heading she was on. So the 20-degree angle is being measured from the vertical, from the north, right? She was going north, and then it says she turns towards the east 20 degrees. Not 20 degrees above east, but she was going north and turned 20 degrees towards the east and kept going. How far? 2 kilometers, okay? So we want to find out how far she is from her starting point. We're going to use vectors to do that. The displacement vector is going to help us here. We've got 2 displacement vectors, right? We've got a first vector, okay? That's 3 kilometers north. Okay. How should we, now, to work with vectors, north, east, south, and west doesn't work very well, right? So we could call north the positive y direction. Like we could change this into like this is an x and this is a y. Now if you've done navigation for airplanes or boats or anything, you know that north is 0 or 360, the east is 90. Like compass directions are rotated a bit, okay? But in mathematics, 0 would be east, north would be 90, west would be 180, right, 270 going around the standard unit circle. So let's work in the standard unit circle here. This would be 3 kilometers at 90 degrees. I'm not trying to get 90 degrees attention on Discord. It's just the direction at, right? Simple. Meaning it's original. Okay. Now, this one is 2 kilometers, but what angle is it pointing at? Okay, you could say 20 degrees east of north and be correct. But if we're referencing from the x-axis, what angle would it be pointing at? 70 degrees, right? Okay, so whichever way you want to do this, or 70 degrees, right? Those are the same thing. Be careful with directions on these things. I'm actually going to just use the 20-degree angle to make this as challenging as possible for you so you can see the possibility and power of everything that's going to go on here. We want to add these 2 together to be able to get this resulting displacement. And the way we're going to do it is by components, okay? So in the x direction, I'm going to take the x component of the first vector, and I'm going to add on the x component of the second vector. In the y direction, I'm going to do exactly the same thing. To add vectors together, you add them component by component. Okay, so now I need to find out what my components are. What is the x component of the first vector? How much of that 3 kilometers heading due north?
0.
It's 0, right? It doesn't have an x component. That's nice. Okay. And how much of that vector is in the y direction? All of it, right? So it's just 3 kilometers. Okay. All right. B is a little bit harder, right? So what I like to do is I'll do it over here. What I like to do is I like to draw like my vector off to the side with my angle, and then draw my components along this miniature. If I try to do that on my drawing over there, it's just going to get really confusing, right? Okay. So this is my angle B. I know it's 2 kilometers long for its magnitude. This is my x, and this is my y. I want to use that 20-degree angle. I want to find bx. That's going to be b, or 2. And then am I going to use sine or cosine? Sine. Why is it gonna be sine? It's not touching the 20-degree angle. Now, if you'd used 70, what would you have used? Cosine, because the 70-degree angle would have been in here, right? Okay, so whichever one you want to choose, but I like to just go with touching, not touching. It's going to be sine 20 degrees, and by is going to be 2 cosine 20 degrees. And I know it's cosine because it's touching the angle. If you want to go through SOHCAHTOA on your own time, that's your business to prove that this works, but it does work. Ashton! This is what happens when my Physics 2B students stand out in the hallway.
What?
Does touching, not touching work?
Yes.
Ashton survived Physics 2A.
Cosine is touching because cosine needs consent.
I had never thought of it that way. Very nice. All right. So now we're going to go in here and we're going to add this together. AX is 0 plus 2 sine 20 degrees. And this is going to be 3 plus 2 cosine 20 degrees. I think I've got the numbers for this. I'm not sure. I do. This bx was equal to 0.684 and by was equal to 1.88. So this turns out to be 0.684, and this one turns out to be 3 plus whatever that number is, 4.88. Okay, so now what we have, okay, is the components of the resulting thing, the resultant. It's 0.684 along the x-axis and 4.88 along the y-axis. So I know that this vector goes 4.88 up and it goes 0.684 sideways. How do we find the length of the hypotenuse if we know the two legs? Yeah, old white dude, right? Pythagorean theorem? 0.684 squared plus 4.88 squared gives me 4.93 kilometers. And then if I want to know the direction, unfortunately, I do have to use inverse tangent. 4.88 all over 0.684 gets me 82 degrees, okay? Now that 82 degrees is measured right here, right? So that would be 8 degrees from north if you wanted to put it that way or whatever, okay? So 4.93 is the displacement. 82 degrees is referenced by standard mathematical coordinate system. Vectors is trig. Trig is vector. The reason you need to know trig is to be able to pull off vectors. We're going to be doing a lot more with vectors, especially in chapters 4 and 5. Those are big, heavy vector chapters. So get the homework done. When we move into chapter 3, we're going to kind of use vectors in a simplified way, and then they're going to come back after the first exam, right? So I will see you tomorrow for lab. Be sure to read the lab ahead of time. Be ready to measure the acceleration due to gravity.